Okay, so yes, as I was saying, first, thank you very much for the invitation. And I just want to mention that a while back I was at a conference and I heard someone talk about the gentle giants of optimization. And I didn't really know what the discussion was about, but as a junior faculty, this sort of rang very true. In a sense, in optimization, the leaders of the field have a very benevolent and constructive attitude. And this means that the field itself is led by sort of gentle giants. And this makes for a very, very wonderful research atmosphere. And so I just wanted to say that today I'm very happy to celebrate Yuri, who is clearly one of the gentle giants of optimization. So the talk today is not going to be about complexity, but about some sort of interesting geometrical phenomenon related to convex optimization problems. And what I'm going to discuss today is a joint work with Armin Ascari and Laurent Elgaoui at Berkeley, and Quentin Rebjerg, who is now at EPFL as a PhD. And it's related to what happens when you take the Minkowski sums of sets. So just a quick reminder, if you have two sets X and Y, their Minkowski sum is the set of vectors written X plus Y for X in X and Y in Y. So this is an example where you have two polytopes, P and Q, and their Minkowski sum is also a polytope P plus Q, and it's a slightly larger one that looks like this. And a very important property that we're going to use a lot in these slides is the fact that the convex hull and the Minkowski sum commute. And so that the convex hull of the Minkowski sum of sets VI is also the Minkowski sum of the convex hulls of the VIs. And so why do we care about this today? Well, it turns out that an interesting phenomenon appears when you take Minkowski sums of sets taken the L1 half ball on the left over here. And I'm computing its average with that. With 2 balls, you get this set over here, this one. When you do that with 10 balls, you get this set over here. And if you do that for a larger and larger number of sets, and you move closer and closer to this set here, which is the L1 ball, which is also the convex hull of the L1 half ball. Right? So in this simple example, we see, and this is true for the mean. It's also true for the sum of arbitrary sets who have about the same size. So if I take digits, for example, in machine learning, that's a classic way to start a talk, and you consider these digits as point sets, and you take the Minkowski sum of the set 1, the set 2, the set 3, the set 4, and the set 5, the set you get looks like this, roughly speaking. I'm saying roughly speaking because this was obtained by sampling. It's very computationally heavy to compute. Arithmetically, of course, it looks like 0. It's not that close to the truth, but geometrically, it's very interesting, right? You take the sum, the Minkowski sum of sets that are far from being convex, and what you get, even with only 5 sets, is very close to being convex, right? And it turns out that this can be quantified fairly precisely, and that also the intuition behind this phenomenon is fairly simple. Why? Well, if you take C an arbitrary set, and you look at what you get when you take the mean of n times C, basically, well, these are points that can be written as the sum of ni over nxi, where xi is repeated ni times in the sum. And this very much looks like a convex combination of points in C. And so it makes sense that this mean here will converge eventually, when n is large, towards the convex hull of the set C. And when you apply this to a set C, which is itself the mean of I arbitrary sets Ci, what you show is also the fact that the mean of Ci's converges to the convex hull, the mean of the convex hulls. Okay? And so, in fact, this can be made completely quantitative, and so if you, this was shown by Shepli-Folkmana and in a paper by Starr in 1969. So they didn't really publish the result, but Starr did. and also simultaneously by Emerson and Greenleaf in 1969. And what they show is that if you take n sets vi in a space of dimension d, and you take a point in the convex hull of the Minkowski sum of these sets, then you can also write that point as the sum of d points in convex hulls of the sets vi, and then the remainers are in the original sets. Why is this what we want? Well, it turns out that in this case, when n grows very, very large, so the number of sets grows very, very, very large, and d remains fixed, this term here on the right will completely dominate the sum. And if this term dominates, because these are sums of points in the original sets, it turns out that the convex hull will become arbitrarily close to the original Minkowski sum, right? So this is what we want. And the proof is very simple, so let's do it. It's basically a direct consequence of Kara theory. If x is in the Minkowski sum of the set vi's, then you can augment x to show that x together with the vector 1 must be written as a conic combination of points of vi, j, ei. And the second half of the constraints basically are normalization constraints. And this is a conic Kara theory representation. You can invoke conic Kara theory to get a representation with at most n plus d non-zero coefficients. And then you simply use a pigeonhole argument. You need at least n points, n coefficients that are non-zero, one for each of the sets vi. And then you're only left with d non-zero coefficients to spread out among the n sets. And what that means is that wherever you only have one non-zero coefficient in the convex combination is trivial, and the point itself is in the original set. And so this means that you have at most d points for which you are in a non-trivial convex combination, and that's how you get the result I just cited. So basically, Shepli-Fokman is just an immediate consequence of conic Kara theory. And more importantly, in fact, the sparsity of the conic representation controls the quality or the distance between the convex hull and the Minkowski sum itself. So this means you can show convergence rate for the distance between the Minkowski sum and the Minkowski means, and its convex hull. This is bounded above by this coefficient here divided by n, where n is the number of sets. So again, you get convergence towards the convex hull whenever the dimension d is fixed or negligible compared to the number of sets n. This is true for the Hausdorff distance, but it's true for many other measures of non-convexity, in particular the volume deficit between the set and its convex hull. And there's a very nice paper by Fradelizzi and others in 2017 going through a number of these non-convexity measures to show convergence. So why do we care? Geometrically, it's an interesting phenomenon, but at this point, it's just that. Why do we care? Well, we care because this also allows you to write duality gap bounds for separable problems. So to simplify the analysis, I'm just going to detail the general idea on a very simple template of separable problems where you minimize the sum of fi xi. So there's one block of variables per function in the sum, and you have a number of linear constraints, right? So if you take the dual twice up to some technical conditions, you get a problem that has a very similar format where, in fact, the functions are replaced by their convex envelopes, okay? So again, we're in a separable scenario. The linear constraints are separable, the objective is separable, and we see that in this case, we can say something about the convergence of the problem towards, convex relaxation towards the original problem itself. And one of the key points behind this convergence is the fact that geometrically, the convex envelope and the function itself match at extreme point of the epigraph of the convex envelope. And so geometrically, we know that when we are at an extreme point of this epigraph, the relaxation itself will be tight, okay? And we can define the lack of convexity as the max distance between the function and its convex hull. And we use that to quantify the duality gap bounds in what follows. So the classical example of this is the relaxation of the indicator of 0 by the absolute value, which gives you, for example, the L1 relaxation. So just one last construction before we get the result we want. We can write the epigraph of problem P as in, for example, a paper by Le Maréchal and Renaud in 2001 in this format. And in that case, the dual simply maximizes an affine form over this epigraph. And basically, very roughly speaking again, the non-convexity of this epigraph controls the duality gap. And so very roughly speaking, again, if G star is equal to G, there is no duality gap in P. So why do we focus on the epigraph? Well, it turns out that when the problem has the particular separable format I just detailed, we can form these elementary epigraph blocks here, Fi, which are just the block components of that form the overall problem epigraph. And in this case, the epigraph can be written as a Minkowski sum of these elementary blocks. Okay? And so now we get back to familiar territory. What happens in this case is that if the dimension of the problem is fixed, and in here, because we're talking about epigraphs, the dimension is the number of constraints, and the number of terms becomes very, very large, then Shepli-Fokman will tell us that the epigraph of the problem becomes closer and closer to its convex hull, right? And in fact, Shepli-Fokman shows that f star star of xi is going to be equal to f of xi for a certain xi you have to find. It's not going to be true for all of them, but for some of them it will be true. For all but at most m+1 terms in the objective. And so that means that the relaxation is tight for all these terms, except for a small residual of f+1. And if m+1 is small, so if the number of constraints is small, then the duality gap will be small. And in fact, you can show directly that if n goes to infinity and m over n goes to 0, the duality gap becomes negligible. So that I introduced all these ideas in a very simple setting where the constraints were linear, etc. But in fact, this also applies in more generic problems where the constraints themselves are not linear. And in that case, you can write a sort of master result in terms of a perturbed version of the original optimization problem. And the perturbation is controlled by a parameter u, which appears in the right-hand side over here, right? And so this master result can be found, for example, in Eklund and Temam in their book in 1999. And it shows that, again, the gap between the original problem and its relaxation will be controlled by this parameter p bar j, which itself, it's a vector of perturbation bounds. And it's proportional to m+1, the number of constraints, and the maximum non-convexity of the functions gij. And what you can show is that HP of p bar star star, so the relaxation taken at this perturbation vector p bar, is the lower bound on HP of p bar, which is the original optimum problem solved at the perturbation p bar, which itself is below HP at 0 star star, so the relaxation at perturbation 0, plus a gap controlled by m+1, the number of constraints, and the maximum non-convexity, right? So we have everything we need here. HP star star is something we can compute. M+1 is just the number of constraints. Max non-convexity is something we get from each function term. So we can quantify the gap very precisely. And we sandwich the original problem between two of these problems we can solve efficiently. Reconstructing primal solutions is another story, and I won't have time to discuss it at length today, but at least we get a bound, and a very explicit bound on the duality gap. So why is this useful? Is this something we can apply to interesting problems? And the answer turns out to be yes, and it turns out that this result is more flexible, and in fact a lot more flexible than you might initially expect. So I'm just going to illustrate an application of this result to feature selection, where this sort of separable setting and high-dimensional setting shows up very naturally. So what is feature selection? It's just a few words, but the idea is just to reduce the number of variables while preserving classification performance, right? So you're in a classification problem, you have a lot of data, and it's very high-dimensional, and it turns out that in most cases, a lot of these variables are just act at least as noise in your prediction problem. And to improve test performance, you want to get rid of these variables that are irrelevant to your classification task. And this will improve test performance because useless variables typically act as noise. So when you get rid of them, the performance improves. But it's also important because it helps interpretation. And so if you can sort of preserve most of your classification performance with a very, very small number of variables, this makes the results a lot more actionable and easier to understand. You get a lot more structure out of your problem. So these techniques are very popular in machine learning, and methods like lasso, L1 logistic regression, RFE and SVM, etc. Solve it, try to solve this problem relatively efficiently. And the reason why this is popular and why this works in practice is that in many natural data sets, there is a very good trade-off between sparsity and statistical performance, meaning that typically a small fraction of the variable explains a very large fraction of your information. And this is the classical 80-20 rule. So 20% of your variables will explain typically 80% of your signal. And it comes up in many, many scenarios, hence the popularity of these techniques. So this is an example of this trade-off curve in gene expression data sets. It's used also for, again, just interpretation and visualization. And so this is another example of feature selection in fMRI activity, results from a team at INERIA called Parietal, where they try to locate brain activity in certain regions of the brain when a patient is performing certain tasks inside classification tasks, for example, inside an fMRI machine. And so the idea here is the signal is very noisy, but you want to detect a certain number of key regions that are heavily associated with these tasks. There is one caveat with feature selection, which is that, in fact, you're choosing between an exponential number of hypotheses, right? You're selecting k variables in a set of n of initial variables. So you have an exponentially large number of hypotheses to test, but typically your data set is of reasonable size, like polynomial. And so there's a massive potential for false discoveries. And when these large fMRI machines first emerged, people got crazy in these experiments where they put patients inside them and ask them to perform tasks and discover associations between regions of the brain and activities, etc. And they failed to control for these false discovery phenomena. And so there are a number of authors try to illustrate this caveat by doing a very simple experiment. So they put a dead salmon inside one of these fMRI machines, and they asked the dead salmon to perform a certain number of classification tasks, and then they recorded the activity in the dead salmon brain. And sure enough, because of the statistical noise, they did find significant activity in the dead salmon. And of course, this was just pure false discovery, but it was a very direct way to illustrate the fact that basically feature selection is an inherently dangerous statistical process if you don't control for false discovery. So just to focus on one way to do feature selection, there are many of them, linear models, etc. But we focused on one which is very, very simple, which is just a variation on naive Bayes. So naive Bayes model, the naive Bayes model calibration problem or maximum likelihood problem is very easy to write. It looks like this. And what's interesting is that if you look at the objective of this likelihood maximization problem, it's separable in the variables theta. And here the vectors f plus and f minus are just the sum of the positive and respectively negative feature vectors. So it's a very simple maximization problem, concave maximization problem, separable in the parameter theta. What is less commonly known is that behind the solution there is a linear model that looks like this once you've computed the maximum likelihood solution, where the vector W is simply the difference of the logarithms of the probability vector theta plus and theta minus, right? So if you want to perform feature selection in naive Bayes, it's totally direct. You just try to find a vector W that has a large number of coefficients equal to 0, meaning that you solve this calibration problem, this maximum likelihood problem, where while imposing that a lot of coefficients of theta plus and theta minus are equal. So this is what the sparse version of naive Bayes looks like. It's the original maximum likelihood problem with the additional constraint that the L0 norm of theta plus minus theta minus is smaller than k, right? It's a simple variation, but now, of course, it's a lot harder. It's a non-convex problem. It has combinatorial features. It doesn't look like, I mean, potentially it's directly related to subset selection and potentially NP-hard, so this is hard, right? And so the key questions are, can we form a convex relaxation, and can we get good approximation bounds on the solution of these relaxations? And it turns out that in this case, we're lucky because the dual is very simple, right? And so basically, the dual is a maximization problem in dimension 1, where you try to solve, sorry, a minimization problem in dimension 1, where you try to solve the minimization of sk of h of alpha, where alpha is between 0 and 1 and is your single problem variable. And sk is just the sum of the k entries of its vector arguments, the top k entries of its vector argument. H alpha is this sort of lengthy function of the input feature vectors and the single variable alpha. And so that's something you can solve by bisection, and the complexity is proportional to n plus k log k. And when n is much larger than k, which is the typical scenario, basically the complexity of solving this convex relaxation is directly comparable to the complexity of solving the original problem. So that's fine. We have a convex relaxation. It's super easy to solve. The complexity does not really increase, basically, when n is large. So computationally speaking, this problem is not much harder. At least the convex relaxation is not much harder than the original problem. But now the question is, can we find good approximation bounds? And it turns out that the answer is yes here too. And that basically the sparse naive Bayes problem I just mentioned falls exactly in this template by the master result by Timmerman and Eklund. And this result gives you very nice approximation bounds relating the optimum value phi k of the original sparse naive Bayes problem and the optimum value of its relaxation, right? Which is this one-dimensional problem I just mentioned. And what's interesting here is that basically Shepli-Fokman means that phi k is sandwiched between psi k and psi k minus 4. And so what happens is that whenever the function psi k becomes flat, then the relaxation is tight. And from a statistical perspective, this is fairly intuitive because basically the function psi k becomes flat when you're starting to add variables that are useless, right? Because you add a useless variable, the objective of your maximum likelihood problem is not going to change that much. The function will sort of plateau. And when that function psi k plateaus, basically you know the relaxation is tight. So this very simple and direct application of Shepli-Fokman tells you that basically this convex relaxation is tight as soon as you're entering a regime where the variables are useless. We can extend this result to lasso-like problems and logistic regression as zero constraints. And so I'm not going to go into details, but a similar result applies as soon as your model itself has a limited rank. And you get bounds on the duality gap that are proportional to the rank of your underlying model, and you can extend these bounds to the numerical rank itself. Right? And so you can basically bound the duality gap between the lasso problem or the sparse logistic regression and their interval relaxation. Primarization is tricky, and I won't have time to discuss this today, but this is the trickiest aspect of applying Shepli-Folkmana to these problems. Reconstructing a good primal solution is not something that's immediately obvious in these cases. And so we can have another result that looks very much like the one on naive Bayes. This one basically also shows that for lasso and sparse logistic regression, for example, the optimum is sandwiched between the value of the relaxations at a certain sparsity k and a sparsity penalized by the rank of the underlying model, right? And in this case, you reconstruct a primal solution by solving a linear program. So what's interesting is that this Shepli-Folkmana and geometrical statement gives you results that are very complementary to what you get with lasso. So for the interval relaxation, you only need low rank, right? For lasso, to at least to show optimality. For lasso, you need RIP and incoherence to show optimality. In this case, you don't. However, of course, if you want support recovery now, you do need RIP even for the interval relaxation. So the Shepli-Folkmana result will take care of optimality, but it won't take care of support recovery. And that's where the difference is. On the other hand, both have similar computational complexity. And so there's no real difference there. So I'm just going to finish by illustrating these results on a few numerical experiments on text. And the idea with text is that feature selection will simply extract important words. And so it's very easy to see if your model is producing something meaningful or not. And so we've used a number of large text data sets to test our results and bound computing times. And it turns out that basically just with a very simple implementation of the code in Python on a regular machine, the computing time is basically 1 second per million variables, which is kind of reasonable. And we try to compare the trade-off between training time and statistical performance for many of these feature selection techniques. And the idea here is that we do it in 2 stages. In the first stage, we use various feature selection techniques to isolate important variables. And then in the second stage, we use the selected variables to solve these classification problems. And we compare statistical accuracy for each of the selected variable sets. And so the idea being that if the feature selection stage has worked well, you're going to preserve much of the statistical accuracy in the second stage. If feature selection has not performed well in the initial stage, accuracy will suffer in the second stage. So we use the same method to solve the classification problem in the second stage. The only difference between all of these experiments is the way we select the variables at the first stage. And what you see is that there are basically 3 clusters. There are very, very fast techniques that use basically univariate ratios to measure the importance of variables. And this is what you see over here. And what you see is that the statistical accuracy falls very quickly when the sparsity increases. And on the other hand, you have a second cluster of methods that are these classical techniques like logistic regression with L1 penalties, lasso, etc., that have a much higher computational complexity, but preserve much of the accuracy at the second stage. And then this sparse version of naive Bayes is somewhere in between. It's 2 orders of magnitude faster than lasso and logistic L1, but it preserves pretty much the same amount of statistical signal. And so at least on these text examples, it does quite well. we've tried it on genetic data sets, and it's not doing as well, but it's probably because the model is not appropriate and we need a little bit of pre-processing. But at least on text, the difference is pretty striking. This is a quick illustration of the result on the duality gap and the statement I've made earlier. So this is these are the upper and lower bounds on the optimum value for various values of the target cardinality. And what you see again is that you have this trade-off curve between number of variables and function objective value, and that at some point it's going to plateau. And when this function plateaus, the duality gap bound becomes tighter and tighter. So this is on the left is an example in dimension 30, and this is another example in dimension 3000, where you see that the duality gap is negligible. Same thing with lasso on the left, and L0 constrained logistic regression on the right. We get these similar bounds that vary with either the target cardinality or the penalty parameter in lasso. And you see that these bounds get, again, increasingly tight as the sparsity increases, and typically you're adding useless variables. So that's a synthetic example where we had everything. And then finally, we also tested scaling, so the computational time versus problem size. And you see here at least that in this implementation, the complexity looks sublinear, but basically is very close to being linear as advertised. And just because, this is feature selection, it's something that should be done at scale. We tried this on a very large digital marketing data set from Criteo, from conversion logs. It's 45 gigabytes, 45 million rows, 15,000 columns. And just to give you an idea of the orders of magnitude, pre-processing, so handling nans, encoding categorical features, etc., takes 50 minutes. Computing the vectors f plus and f minus takes 20 minutes, the feature vectors for the naive Bayes problem. And computing then the full trade-off curve, so target sparsity versus, computing basically 15,000 sparse naive Bayes problems takes 2 minutes, right? So basically we've reached a point where, at least in this simple experiment, the feature selection computational complexity is negligible versus that of just pre-processing the data set. So I'm done. So basically, if you remember just a few things from this talk, is that the Shepli-Fokman result gives you very explicit and simple duality gap bounds for separable problems. And then this allows you, it's flexible enough to allow you to get very generic results on the quality of the solution of lasso relaxations, for example, or L0 logistic regression, with no RIP-like assumptions, okay? So of course, these are statements about optimality, not support recovery, but they're still interesting. And they mean in particular that for naive Bayes, we basically get sparsity almost for free. And this works quite well from an empirical perspective, and is very effective in practice. So there are a few papers on this on ArXiv and at AI Stats, and we have a code online if you want to test this empirically. I'm done. Thank you very much again, and sorry for the weak signal.
Thank you. We just have a time only for maybe one questions, because it's how to say, we have a lunch and it's.
Yes, I understand the lunch concept very well.
Sorry, yeah. Okay, maybe one question from Zoom colleagues. Okay, from this room. Okay, sorry for the timing. It's unfortunately it's too late. Okay, Alexander, thank you very much. It was very nice and unexpected somehow.
Yes.
Yes. Thank you. Let's thank the speaker again, and continue after lunch.
Continue after your lunch.
Thank you. No, sorry. We continue next day because we have, according to schedule, next talk on next day. So today's session is finished. Okay. Goodbye and see you tomorrow.
Bye.
Bye. то сейчас набегут, да, студенты, которые... У нас есть 40 минут, но появится через 10 минут там очередь, поэтому я рекомендую сильно не тормозить и прям вот в столовую.